Ja, jetzt haben wir das Vergnügen, einen internationalen KI-Vordenker zu begrüßen. Ramin Hasani ist Mitgründer und CEO von Liquid AI. Er forscht am MIT Seaside und er hat mit seinem Liquid Neural Networks gezeigt, wie KI nicht nur größer, sondern eben auch smarter gemacht werden kann. Und sein Keynote-Titel heute lautet Intelligence for All. Und darum geht es auch, wie wir KI so gestalten, dass möglichst alle davon profitieren. Ich bin sehr neugierig darauf, was er uns jetzt erzählen wird. Und bitte begrüßen Sie mit mir Ramin Hasani.
All right. Hello, everyone. Thank you very much. All right. Let's get started. I want to tell you today, I want to give you a new perspective given the whole discussions about AI sovereignty and the hotness of the topic in Europe right now. I want to give you a new perspective, introduce you to a new product, a new technology, that how we can approach AI sovereignty. And how can we put AI in the hand of everyone? And then tell you a little bit like, what are the opportunities on top of this technology that we can bring to people? So, as you all know, I don't want to bore you again, but we are in this remarkable era of intelligence. So, AI is changing everything around us. AI is allowing us to discover new drugs. AI allows us to discover new material, new physics, new math. AI is changing everything. And it has a lot of, I'm a techno-optimist. I have a lot of expectations from AI as a person that has been like in this field for the last probably 12 years. I can tell you that the technology has massive amount of promise. But also, it comes with challenges. So some of the most fundamental challenges of AI is the fact that, as you know, we started making AI systems larger, and they started getting better, and they started communicating with humans, you know, with the new ChatGPT era. And as you see, like the energy footprint of these AI systems also growing, demanding a lot more infrastructure cost and investment into building massive data centers to be able to host these new type of intelligence systems. And as a result of that, a byproduct of that, we have sustainability matters to pay attention to as well as the systems are getting more complex, and we need to be able to have proper measures in place in order to be able to tackle these problems. But before getting there, I like to think about problems from first principles. So I want to ask the question, what is the fundamental reason why AI is actually, you know, exponentially difficult and exponentially kind of demanding more and more energy? So the answer comes to the source, where the AI is actually coming from. So the building block, the unit that actually allows you to build a generative AI solution is a technology called transformers. Who has heard about transformers? Okay, good. So so you basically put these blocks of computational blocks next to each other. You replicate them a bunch of times. You build a large billion parameter or trillion parameter AI system that allows you to build a text-based AI system or a vision-based or a combination of all of these things with audio exchanges. The problem with this fundamental technology is that the more data these computational blocks consume, the more energy, exponential amount of energy is needed to process more and more information. So the graphs that you see here, on the x-axis you see basically the amount of data that you feed inside the system, and at the y-axis you see the demand for computation, the number of flops. So what we wanted to think throughout decade-long of research, can we do better? Can we find a solution? Can we look into natural learning systems? can we look into physics to really discover a new type of intelligent system that allows us to systematically reduce the cost of AI systems. And we did just that. What we discovered through years of research in Austria, actually at Vienna University of Technology and at MIT, we have discovered a new set of algorithms that allows you to substantially reduce the cost of these AI systems. So one of the things that you see in this graph that I'm showing, the liquid model, the purple line there, it actually substantially reduces the amount of energy as you consume more and more data. This has fundamental implications for us. This is now an efficient form of AI system. So I'm going to tell you what is getting unlocked, what is the impact of this efficiency. We need these large data centers because AI consumes that exponential amount of energy. But with efficiencies unlocked, we can actually give rise to a new set of markets. This is what I like to call this device AI. Device AI is the ability to perform or put the most complicated versions of AI systems on a CPU, on an NPU, or on a GPU outside of data centers. So you could, because of the efficiency gains that you would have at the algorithmic layer, you might be able to get AI systems to run on a Raspberry Pi, on robots, on laptops, on phones, on cars. So if you actually have efficient systems, efficiency can unlock for you this new whole set of AI systems that is actually in our hands. 99% of the chipset in the market right now is actually outside of data centers. So there is an opportunity here that we can actually use. Efficiency also has implications for the cloud-based AI. You can actually use efficient ways of computation to actually build really, really fast AI systems in data centers. So what does it tackle? If you think about device AI, it actually goes through the three kind of concerns that we have in Europe. For example, on the energy side, the global data center market is going to reach, we're going to build 130 gigawatts of power by 2028. So if that's the case, like where are we going to get that much energy? So there's a lot of concerns about that. But we also, alongside this kind of progress on cloud and building like the infrastructure for the cloud, we could also start looking into the lightweight way of using the chipsets that are available already for us. We can use the existing silicon. We have powerful silicon companies already in Europe, so there's an opportunity here to use this and bring these algorithms that I was mentioning to enable device-level AI. One of the impacts of bringing computation on device is privacy. Data never leaves the device. So if computation happens directly on the device, privacy is preserved. Also for regulatory matters, you're not centralizing profiles of people, so you also have like a lot of defensibility there. At the same time, you can actually build sovereign products building on top of device AI foundations. So with that mission, this became kind of the mission of Liquid AI, the company that I actually built. We are building these efficient variants of AI systems, and these are general purpose AI systems that can process text and signal and vision and audio and process all of those and be able to deploy them at any scale. So basically, we try to bring in this cost of intelligence much lower so that you can host them on any possible devices that is available around us. How we do that, it's a very complicated technology, but essentially, just to give you an idea about what we did to design these systems, we designed an AI to design AI. Okay, so we designed a huge search space of possibilities. This space included a lot of computational blocks that have the potential to give rise to general purpose behavior. Attention transformer is one form of that. we learned from brains that there are many different other mathematical operators that you could use and build it in this blend and then search through the space, give this AI, massive AI system, it's a search-based system. You give it a goal. The goal is that given this device that is in the loop, find me the best mathematical operators or the fastest mathematical operators that give us the highest performance on a certain device. So we have a meta algorithm that designs AI for us. This way, we didn't put a bet on a single architecture. We didn't just want to put like, oh my God, we learned something from the brains, and that's basically the God formulation. But we actually like searched through the space of possibilities to really fundamentally understand what should be that fundamental building blocks. And for every given silicon, a new architecture emerged. So that means, given a silicon, you can optimize an architecture and basically bring back that architecture that performs a task-specific job as good as, guaranteed to be as good as anything else that is basically out there, but substantially reducing the amount of energy consumption. We are a foundation model company as Liquid AI, meaning that we have like 6 different pipelines for designing AI systems. There are a lot of sophisticated algorithms goes in place. One of those algorithms is that AI that designs AI that I mentioned. That's on the architecture side. We train models, we curate data, we post-train models, we then put these models in production. We bring them down to basically have the best language base possible for a given silicon. If it's a CPU, if it's a GPU, or an NPU, you can actually implement these systems on top of those. Let's talk about some of the numbers. The gains that we are talking about, the more information these systems that we design, the more information they process, the more savings they generate. The reason is that the alternative architecture has an exponential raising kind of cost, but our solution has a linear, pseudo-linear kind of cost as they process more information. So this is basically on the training side, you can substantially reduce the amount of energy and also capital that is needed for training foundation models. At the same time, you can give rise to models that run on silicon the fastest possible way. So as I told you, we search through the space so that we can actually find the algorithms that give rise to the fastest possible execution. So we have, compared to the models generated by Google, Microsoft, and the Chinese labs that are actually very active these days in this scene of foundation models, we actually have like 2x to 3x speedups on a given silicon. Here I show like many different silicon providers like AMD, Apple, Intel, and Qualcomm. You can actually expect to get up to 5,000 tokens per second on a CPU on a laptop. So that means like you can process information extremely fast just on a silicon, on a CPU. And these models actually already fly on GPUs. So we carefully look at how to create these models. We ship these models that we call liquid foundation models, the result of that architecture, like the products that are coming out of the company. We ship them in a way that even third-party people, they can take it and they can optimize it on silicon. For example, here is a third-party optimized version of a liquid foundation model, a text-based liquid foundation model that runs directly on the phone. And you can see the difference between a CPU implementation and an NPU implementation here. NPU is a neural processing unit that all of your phones, if you have an Apple phone or a Samsung phone, you actually have it like integrated in your phones. And you can actually receive a really fast implementation, a very efficient way of using this AI system while data never leaves your premise. So that's something that you can use. And also, when we are talking about running a system, running a complex algorithm, this algorithm has 1.2 billion parameters. You're running 1.2 billion parameters on a CPU on a device, so device get heated up. So you want to do temperature control, so that also becomes extremely important. So there are a lot of matters that comes into like implementing AI in practice. We have a range of liquid foundation models. They're not just text-based foundation models. These products range from text, vision, audio, and specialized applications. We basically build a library of available models, and we provide them. Some of them are open source available, and some of them are B2B. We work with some of the clients and provide them with the fast and the best-in-class models on device. I want to show you an example of an audio to audio. It's a multimodal foundation model in action. Like, what kind of functionalities can you expect for an on-device version of an AI that delivers the same qualities of ChatGPTs of the world, but this time, like, it does all the computation directly on a small, very, very tiny silicon. Let's look at this one.
Hey Lily, I wanted to introduce you to some new friends. Tell us about yourself.
Hey there, I'm Lily, your edge-focused voice assistant, and I am here to chat whenever you're ready. I can answer questions, give advice, and help you plan things, all right on your device. What would you like to start with? Entropy is a measure of a system's disorder or randomness. So higher entropy means more possible microstates. Does that help?
Can you give me an example from everyday life?
Sure. Imagine you leave your bedroom untouched for a week. Over time, dust, clutter, and stray items pile up, making the space feel messy and chaotic. That extra mess is a clear sign of entropy, the natural tendency for things to become more disordered.
Let's mark QA and UAT as immovable milestones. Everything else is flexible. But exactly. Let's set a decision checkpoint. If we don't have all specs by the end of this week, we'll escalate to the client and propose trade-offs.
Good call. That way, we're not scrambling at the last minute.
This AI system fits on a $60 CPU. So you can actually buy a Raspberry Pi, and you can actually put this thing and start like using AI. So that's the impact that we're talking about here. So this is another one, an example of an enterprise application of the coding model that can do the job, complete basically a coding task for an enterprise application directly on device. That's another liquid foundation model. One of the non-trivial breakthroughs that we have recently done is this class of models. So this graph here is very important. We all always want to have access to the best version of intelligence. So we never want to sacrifice it. If there's a better version of an intelligence out there, you always want to talk to that one, So what we thought is that, is it possible to really get these small models that are running on silicon and on device, specialize them for a certain application, and deliver the quality of cloud models? So what you see in this graph here, it's an important graph. On the x-axis, you see the size of models. On the y-axis, you see a translation quality, multilingual translation quality of a text-based foundation model. Now, there's a bar over there that is GPT-4o kind of performance, like as a cloud kind of equivalent. And what we are showing is that a 1.2 billion liquid foundation model, the purple dot over there, approaches the qualities of GPT-4o, which is like almost 200 times bigger than the model itself. So that means you can actually have models that hold probably around 400 megabytes of memory on a device, and they can actually deliver ChatGPT quality for specialized applications. That is very big. We wanted to test it on more samples. So one is translation. We can also test it on other things. So here, it's another, like it's a more complex way of looking at translation, free-form translation, bidirectional between Japanese and English. And you can actually build a translator, this time with a 350 million parameter model. You can actually achieve that quality. Same goes with, let's say, data extraction. One of the applications of, big applications of AI is massive document parsing. You want to actually parse a large amount of text and try to extract information very accurately from this text. So we managed to actually bring the quality of these tiny models to the level of cloud models. And this is very important because now you can imagine on-device AI and agentic AI applications that you want to enable, they can get to those qualities. You can actually replace an OpenAI API model and have your own local model to be able to do the same thing that you're doing. Here we have like masking of personally identifiable information, PII data. You can actually do that. This model is learned to do that in multiple languages. This one is Japanese. In Japanese, it can actually, mask out inside the text personally identifiable information at the quality of a cloud model. We can even boost the agentic performance of these models beyond what is possible on the cloud. So we have been starting to working with a lot of car manufacturers, and they want to have in-car intelligence. So inside the car, there are like certain functionalities that you can enable with intelligence systems, and you want the intelligence to be locally on device. Why? For security reasons, for privacy reasons, for the ability to be always on, so you really have to have intelligence there to be local. For those applications, we can boost the performance even beyond what is possible through the cloud. Applications that they were once imagining, this can become reality. So we built a platform to provide access to all of this information. This platform allows you to download some of these models. If you want to use these things today, you can actually do this, and you can select some of the instances of these models. You can even fine-tune them, because this is going to be fine-tuning one of these models on personal data. It's going to be between $50 to $500 of expenditure. So these are like extremely cheap to fine-tune. And then you can deploy them on any device that you would want to deploy. So what I wanted to show you was basically these ideas of device AI. It is a completely new market. We are taking an angle. We are trying to be as systematic as possible about like building AI systems that can truly go on devices and enable something outside of data centers. Inside of data centers, you can expect these models to be blazing fast, lowest possible latency, and also reducing the amount of energy and carbon footprint that the cloud, like large AI models have. Outside of data centers, you can enable applications where you get those energy benefits, but the fact that you can actually reduce the energy cost, but that much, we bring in this efficiency to the levels that we just discussed, you can reduce this energy and you can put them on CPUs, NPUs, and GPUs. You can host them fully private, secure, and always on, in an always on kind of situation. There's no latency, there's no AWS shutdown that actually blocks your application, so everything is basically around you. So, and then the goal here is that like with the directions that we are taking right now, all of these, just to tell you the scale of where we are today, like by 2027, we're going to be on 500 million mobile phones, which, like instances of these models are going to enable many, many different applications. We're going to be on 100 million laptops, 1 million AI glasses. That's another medium that is actually popping up these days. 10 million cars, and we will be powering over 10 billion AI agents for workloads in private and air-gapped environments. This is what we are talking about until 2027. So this space is massively flourishing for on-device AI. So I wanted to put this on the agenda because we are talking about sovereign AI. We are thinking about the cloud applications, but there is a whole lot of opportunities for us available to bring intelligence for all. So the goal here is to do a plan at the scale, a sustainable and economically viable way to deploy AI in our society. Thank you.